Hello everyone, my name is Yukui Luo. I graduated from Northeastern University and I'm currently work at UMA Statmos as an assistant professor. So today I'm gonna introduce our paper, DeepShuffle, a lightweight defense framework against adversarial fault injection attack on DNN in multi-tenant FPGA. In this video, I will discuss the motivation and the basic idea behind our paper. As we know, the cloud computing has rapidly deployed over the past decade. To increasing the resource usage effectiveness, hardware virtualization has become a significant growth area in cloud computing. However, compared to the mature virtualization technology for CPU and GPU, FPGA virtualization in the cloud is still an emerging topic. Most recently research in this domain focus on enabling resource sharing and achieving multi-tenancy on a single FPGA chip. There are 3 multi-tenant FPGA prototypes already implemented in both public and private clouds. As we know, the FPGA is a hardware programmable device. For security perspective, multi-tenant FPGA may introduce some unique attack surface. Specifically, the sharing of the critical hardware resources, such as power distribution network, enables indirect interactions between the circuit applications of different users. Our previous work, DeepDupe, leveraging supply voltage fluctuation and a set channel guide attack controller to inject well-timed faults at runtime, degrading the performance of DNN modules executing in a cloud FPGA context. In this paper, we are trying to address 2 questions. The first question is, can DeepDupe affect highly optimized open-source DNN accelerator, as it was previously demonstrated using manual-made accelerators? The second question is there a lightweight method to mitigate DeepDupe-like adversarial fault injection attack? To answer the first question, we choose TVM-VTA as our DeepDupe attack target. TVM-VTA is an open-source DNN accelerator that runs on FPGA and provides a compiler to optimize the execution process of different DNN architectures for better performance. We followed the multi-tenant FPGA threat model using in most research to reproduce the target and untargeted attack using ResNet 18 and ImageNet on TVM-VTA accelerator. Our result shows that the TVM-VTA is more robustness than manual-made accelerators. The main reason for this observation is the TVM-VTA runs the first convolutional layer and the last fully connection layer in ARM core, which is outside the FPGA. So here I will say that we will use this new reproduced result as our baseline in this paper. Then, let's go to the second question. The answer is yes. As in DeepDupe, the main idea is to identify and attack the weak transmission packages that most impact the overall inference accuracy. During the normal inference, all transmission sequences are fixed. Therefore, the core concept of our mitigation strategy is to shuffle the weight transmission order, thereby implementing our moving target defense. So, how can we shuffle the weight transmission order effectively? We found some inherent properties of DNN that can help us to implement the shuffle. In the first principle, for our convolutional 2D layer, if we shuffle the weight parameter along the output channel, the output feature maps of this layer will be shuffled accordingly. The second principle is, If we apply active channel shuffling on a convolutional 2D layer, following a specific shuffling rule, the same rule should also be applied to its connected layer in order to maintain the computational correctness in the DNN inference without using any additional operators. The third principle is the principle 1 and the principle 2 can be applied to all layers with trainable parameters. Here we provide some example about how to apply shuffling rule onto DNN architecture. The first example is how we can apply the shuffling rule onto the batch norm layer. The second example is how we can apply them onto the residue block. The third one is how we can apply the shuffling rule onto the residue block with some downsampling layer. The last example is how we can apply those kind of rules inside the dense block. The previous three principles form the basic idea of DeepShuffle. Let's have a visual demonstration to understanding the underlying process of our method. Let's see the basic DNN inference process on DNN accelerator. Here we have an onboard memory. In every inference, we need to buffer the weight onto the on-chip buffer here to compute the output. In normal inference, multiple feature maps serve as the input of a specific convolutional layer. DeepDupe targets a favorable weight transmission point for attack, where this weight performs computation with its corresponding feature map. This feature map contains a significant information about the inference image, making the attack effective and leading the substantial inference accuracy degradation. However, if we apply DeepShuffle, the attack point becomes less effective in subsequent inference rounds. This makes it challenging for DeepDupe to find an effective attack point if we shuffle the weight transmission in every inference. Here, let's see some DeepDupe effect examples. In the first row, we show the original output feature map. In the second row, we show the output feature map with DeepDupe attack. So the first one is the brightness of the fluctuation. The second one, we can see it erases some features. Then the third one, we can see the DeepDupe attack create some features. Those three things will leading to a substantial accuracy degradation at the end. Here we have another example shows the DeepDupe effect for an entire layer. We highlight the feature maps attacked by DeepDupe with 3 different colors. Then let's see how DeepShuffle applied the moving target defense. Here we have a progressive differential evolutional search algorithm in DeepDupe. In the first step, the algorithm will initialize the step and the fitness function evaluation result. Like here, the algorithm will calculate this table, which include the weight transmission ID and the corresponding loss when we deploy the DeepDupe attack. The different things will happen at the third step. Comparing with the DeepDupe attack, the DeepShuffle actually moving the target of the selection, which means in every iteration, when DeepDupe is running its searching algorithm, every time the DeepShuffle cannot have the same result comparing to the previous round. So this is the meaningful things that we need to mention, that DeepShuffle actually is moving the target of the deep dupe and make it hard to find a good point to deploy the attack. Let's introduce our evaluation matrix, DPI, which include the number of evolutions, mutation numbers, the number of attack rounds, and the sample numbers and the input batch size. These effects coming from the deep dupe profiling step. Let's use DPI to measure the rounds of inference that deep dupe needs to finish the search. We perform the evaluation onto 2 different datasets, and they include 5 different DNN accelerators. So here we show the baseline DPI for each of them. Compared with the baseline, DeepShuffle make deep dupe have more DPI for the profiling step. Here is another chart to show what happens when we apply DeepShuffle. After 400 rounds of the attack, applying DeepShuffle to the DNN accelerator still maintains some accuracy in the image inference. We also tested the DeepShuffle performance in targeted attack. Here we use Cipher10 dataset class 8 as the target. The targeted deep dupe attack is very threatening, which can successfully misclassify most target class samples. However, after applying DeepShuffle as the defense method, even after 1,000 rounds of attack, the targeted class still can be detected. After discussing our evaluation results, we want to know more detailed properties about DeepShuffle. So we applied analysis on the DNN architectures. First, we analyzed the feature similarity on the output of the second convolutional 2D layer of a ResNet 18. The green line represents the baseline of the normal inference. With the increasing in the attack rounds, the deep dupe output becomes significantly different from the original output. However, if we apply DeepShuffle, it will mitigate such kind of change. In deep dupe attack, the algorithm can automatically select the target layer. But now we would like to know the robustness of each layer. So we profiling the number of attacks of each layer. This results evident that the attacker can course a drop in the post-attack accuracy to 10% for the inference, regardless of the layer targeted with the deep dupe attack. In ResNet 20, the last layer and the layer 4 and layer 7 are very vulnerable and only needs 30 attack rounds to achieve the random guess goal. Our DeepShuffle method greatly improved the robustness of layer 4, 7, and the last layer. From this test, we identified which layers are still vulnerable when we apply the DeepShuffle. We can apply other methods in the future to address these kind of vulnerabilities, such as redesign the corresponding layers or offloading the workload onto the CPU. However, this may become a task for our future work. So now we can draw some conclusion. First of all, DeepShuffle strives to randomize the well-performed attacking opportunities. The second is the DeepShuffle is applicable across various domains, such as computer vision, natural language processing, and the robotics. The third conclusion is the DeepShuffle works without requiring of the retraining of the model. Thank you for listening. If you have questions about this paper, feel free to send me an email and I'm very happy to answer your questions.